Bismillahirrahmanirrahim. This lecture is going to be a preliminary of a mini series of, let's say, 2 or 3 lectures about prime numbers and how to determine them and some of their benefit and application. Now, I intend to present all these lectures at the developmental mathematics level for the general audience. So let's get started for this introductory lecture. Now, in our early grade school mathematical endeavor, we are first exposed to counting numbers. 1, 2, 3, 4, 5, and so on and so forth. And then later on, when we learn about multiplication and division, we notice that some numbers like 2, 3, 5, 7, 11, 13, and so on, they are only divisible by 1 and themselves only. So we name them prime. We put a name on them. The English language is called prime. Now, since this word carries some properties, then based on those properties that this particular name carries, we make definition. And every definition must be an if and only if statement. Meaning should be a conditional statement. If ... then the converse of that must also hold. So let's put this one in this property of the prime as a definition in if and only if statement. So we can say a natural number is a prime if and only if it is divisible by 1 and itself. So if you put it if then use the converse. You say, if a natural number is prime, then it is divisible by 1 and itself. The converse of that is that if a natural number is divisible by 1 and itself, then it is called prime. Do you follow me? Now, after that, we notice that some other numbers besides prime, like 4, 6, 8, 10, 12, 15, and so on and so forth, those numbers, they are consist of primes, in a sense. For example, 4 is 2 times 2. 2 is prime and 2 is prime. 6 is 2 times 3. 2 is prime, 3 is prime. 8 is 2 times 2 times 2. 2 is prime, 2 is prime, 2 is prime. 9 is 3 times 3. 3 is prime, 3 is prime, and so on and so forth. So when we notice that, we make a conjecture on that early age in developmental mathematics. We make a conjecture that if a number is not prime, it should be product of some primes. Product of some corresponding primes, which means primes that correspond to that particular non-prime number, that particular composite number. So this is a conjecture. But mathematics is a very meticulous subject. And it demands justification based on axioms, definitions, and theorems. So it does welcome the conjecture, but does not accept conjecture as a justification. So we have to make justification. So we cannot use mathematical induction to justify that every composite number consists of primes. Because in mathematical induction, the prime numbers are not located next to each other. They are not standing next to each other, like 1, 2, 3, 4, 5, and so on. As a matter of fact, the further we go, the distance between the prime numbers start to increase. Except, of course, those that they call it twin primes, like 5 and 7, like 11 and 13, 17 and 19. Beside them, the distance starts to increase, so there is no discipline. So the domino effect cannot be applied, which is necessary for mathematical induction. The domino, I repeat myself, the domino effect cannot be applied. So mathematical induction cannot be used in order to justify that our conjecture is correct. So we have to seek for deductive approach, deductive proof, to say that yes, our claim, our conjecture is correct. Unfortunate for us, centuries back, as mathematician has already given proof that our conjecture in fact is correct, is true. And that is called fundamental theorem of arithmetic. So what it indicates, fundamental theorem of arithmetic, he says that every composite number consists, made of, product of its corresponding factors up to the order of the appearance of the factors. You follow me? No, the word up to the appearance of the factors, of the prime factors, plays very important role. Because I forgot also to mention that the theorem indicates that every composite number can be decomposed into product of its prime uniquely, up to the order of what? Of the appearance of the factors, of the prime products. Now this word up to the order of the factors plays very important role. Means up to that point, as the ordinary language is concerned, which means after that point is not of our concern, is not relevant, is immaterial. So it says up to the order, which means we are not concerned about the order. Now if it doesn't say that, if that was not mentioned in the theorem, then the uniqueness will be violated, because then 6 is 2 times 3, and 2 is prime, 3 is prime, and 6 is also 3 times 2. 3 is prime, 2 is prime, and they are, well, you can say that is not unique, which means 2 ways you can present, in this case, in 2 ways you can present a composite number into product of its prime. So when it says up to the order, which means in reality order is irrelevant. So you cannot say the order, hey, 2 times 3 is different than 3 times 2, therefore the decomposition of a prime number is not unique. You can say that, and you can use it as a counterexample. So up to the order of appearance of the factors prevent that to happen. That's the beauty of mathematics. Now, since it is a theorem, has been proven, so we don't have to go through the proof of that unless it is demanded. They say, okay, give me the proof that has been made. I want you also give it to me, the proof of fundamental theorem of arithmetic. That, of course, is outside the subject that I said I will present it on the developmental level. Now, the point is that the theorem does not tell us how to find, how to determine the primes. He gives us guarantee that every composite number consists of product of his prime. I guarantee you. He gives you green light to go ahead. Otherwise, somebody asks us, how do you know the prime numbers, what is it, the product of prime numbers is possible. Maybe you reach a level to a number that number cannot be decomposed. It's a composite number but cannot be decomposed to product of its prime. The theorem says you cannot find such a number. And that is what the meaning of theorem. Because if something is given as a theorem, then you cannot produce any counterexample to violate that theorem, because it has been deductively proven. Okay, then in the following lecture, I intend to give a method of decomposing a composite number into product of its prime in a very efficient and logical manner that I have not seen any textbook doing that. So you can call it Alice technique. And you will find it to be very, very pleasant and hopefully effective. So I will be doing that for next lecture. I thank you as always for watching. And again, as always, I wish you prosperity and good health. And please stay safe. So long.